could do with a product rule, quotient rule combo, correct? But what they'll actually tell you to do is using logarithmic differentiation. So this is called logarithmic. It's in your notes.
We're bad at logs.
It's not very many loggy things. You're okay.
Just yesterday.
So that scares me a little. All right, so what we have to do is for logarithmic differentiation, what you're going to do is you're going to ln both sides. So you're going to go ln of y equals ln of this bad boy. X squared 5x plus 1. Not talking to you, Kyle. I don't have enough energy for that question. 3x minus 2 cubed. And I don't get paid enough to answer it. All right. After we just had a test on logs and lns. Okay. So, Kyle. So, what we learned in 30-1, and this is the only thing we need from it, it's going to be, if we have two things multiplied with a log in front, we can separate them by addition, and if we have something divided, we can separate it by subtraction. Remember with the product and quotient and power law, there's when we have two things multiplied, we can separate it by addition. That's the only rules we need to remember. So, ln of y will stay. The x, okay, you have to stop.
And I'm being so serious. What does it do? I actually do
Log base e. You've been here for like 3 weeks.
log base e.
So we're going to get ln of x squared plus ln of 5x plus 1 to the half minus ln of 3x minus 2 cubed. Okay. So in 30-1 we learned that we can take whenever there's a log in front of something, we can separate it by plus and minus logs by product and quotient rule. Then we learned in order to do the derivative of a ln, we take what's beside it, put it in the denominator, ln base e, derivative in the numerator, right? We talked about that. But right now our derivatives would be kind of ugly because we have these powers. So what we can do, remember we learned this as well, power rule stated that we could take this exponent and drop it in front of the logs by power rule. So we're going to get ln of y equals 2 times ln of x plus 1/2 ln of 5x plus 1 minus 3 ln of 3x minus 2. Now, some people think the derivative is done. I haven't derived anything. I've literally just used log laws from 30-1 to make this in a form that I can actually do the derivative. Okay? So, now we have it in a form that we can derive. What is the derivative of a ln? You take what's beside it, put it in the denominator, ln e. Do I need to write ln e though? So it's only unless it's another log. If it's log base 6, 5, 7, then I have to go ln of 7, 6, 5, whatever it may be. Derivative in the numerator, right? So ln of y. I rewrite the y in the denominator. And what's the derivative of y? Y prime. So y prime sits in the numerator. You should be writing this down. No. Then we have 2 over 1. I'm going to write that as a fraction. Remember when it's a coefficient, we can just keep the coefficient in front. Then what's the derivative of ln x? The x goes in the bottom, and the derivative of it in the top. What's the derivative of x? 1. Plus 1/2. The derivative of ln, what goes in the bottom? 5x plus 1. Now remember, we technically write ln e, but do I need to write the ln e in the bottom? No. And the derivative of 5x plus 1? 5. Then I have minus 3 over 1 The derivative of ln 3x minus 2. 3x minus 2 goes in the denominator. What's the derivative of 3x minus 2? So, the great thing about logarithmic differentiation is there's not a ton of simplifying that you have to do in the end. It'll just kind of look long and arduous and ugly, but it doesn't matter. So we'll bring the y up because we have to get y prime by itself to get the derivative, correct? So we're going to get y prime equals y times this ugly thing, which we will put the numbers together if we can. So 2 times 1 is 2. 1 times x is x. That's as good as it gets. Plus 5 over 2 times 5x plus 1. And we don't have to put them together. We just leave them separate like that. Then minus 3 times 3 is 9 over 3x minus 2. Right? There's one last step that you can't forget. The last step to not forget is you have a y sitting here. And we have a y up here, right? The equation, y equals that. So you have to come down here and replace that y with that ugly fraction. So we're going to have, as our last step, y prime equals whatever our y is. Our y is x squared square root 5x plus 1 over 3x minus 2 cubed. So that's just the y. And then we get 2 over x plus 5 over 2 times 5x plus 1 minus 9 over 3x minus 2. Done. So when you're asked to do logarithmic differentiation, when it leads you to logarithmic differentiation, the first step always is ln both sides, and then get it into a form that you can actually derive. So separate it, put the exponent from by power rule, then derive. Yeah.
When would you need to use this?
When it says logarithmic differentiation. So you use this when you have really complicated ones. So this one, if we didn't use logarithmic, we would actually have to do power rule inside to get our f in the quotient rule.
But like, how would you apply it in like, I don't know, like a word question? Like how, when would you use this other than in this class?
Well, they'll use it in complex equations. Like actual equations that have been made up in the world. There'll be ones where you have like a few polynomials embedded in an equation and you have to solve it by finding it for sure. Like H of maximum. So in economics, they use it for like, what's it called? Cost, maximizing cost and minimizing cost or expenditures, maximizing cost, making profits, stuff like that. So they use it a lot of the time in engineering because they need to maximize certain things. So they'll come with their own equations that come from them, give it to you, and you have to derive it. All right. So we're going to flip to the back page. Looking at the back page. We're coming back to that one because this one's like the last one we just did. Example 5 is a variable base to a variable exponent. So we have done variable bases to numeric exponents, just a polynomial, or to halves or whatever. We've also done numerical base to variable exponent. What do? We rewrite it, long base, derivative exponent. What we have not done is variable base to variable exponent, which is example 5, which we're going to do after. So we're on the back page. It's example 6. It says find an equation to the tangent line of f of x equals x square root x squared plus 3 over 1 plus x at the point 1, 1. So the very first thing you're going to have to do is find m tangent. How can you do that? What is m tangent the same as? Y prime or f prime of x in this case, right? So the first thing you have to do is get the first derivative and then plug in 1, right, to get the tangent. So try and differentiate this first. So ln both sides. All right. So, guys, no. So we're gonna take the derivative of both sides. So ln of f of x, you rewrite it on the bottom. The derivative of f of x on the top, so it's f prime of x equals, oh, I got a little excited. Never mind. Ln of f of x, I need to make some better form. Ln of f of x equals ln of x plus ln of x squared plus 3 to the half minus ln of 1 plus x. The half can drop in front, and then we can derive. So we're going to get f of x in the denominator, f prime of x in the numerator. Ln of x is 1 over x plus a half. The derivative of ln of x squared plus 3 is x squared plus 3 in the denominator. And the derivative of x squared plus 3, 2x in the numerator. Minus, and then 1 over x, 1 plus x in the denominator. And the derivative of x is 1 in the numerator. Bring my f of x over. By multiplying it. And I get f prime of x equals x root x squared plus 3 over 1 plus x times 1 plus, or 1 over x plus, 2's can cancel, x over x squared plus 3 plus 1 over 1 plus x. So that is the same as m tangent. But we want to find it at 1, right? Because we have x and y. So we're going to get 1 square root 1 squared plus 3 over 1 plus 1 bracket 1 over 1 plus 1 over 1 squared plus 3 plus 1 over 1 plus 1. So we're going to get 1 times the square root of 4, which is 2 over 2, which cancels, gets me a 1, times 1 plus a quarter plus a half. What's 1 plus a quarter plus a half? What's a half plus a quarter? Oh, there's a subtract. Good call. Subtract, subtract, subtract. Okay, what's 1 1/4 minus a half?
Negative 1 1/4.
No, what's 1 1/4 cups? Subtract half a cup.
Yeah, negative 1 1/4.
1 1/4 cup is this big cup. It is 1 1/4 cup. And you take a half out of it, you don't have negative cups. 3/4. We have 3/4. Y minus 1 equals 3/4. Don't bake. That's all I said. X minus 1.
You said 1/4 minus.
No, I said 1/4 plus. I said 1.
1/4 minus a half.
Oh, sure you did.
That's right.
We're gonna reel back the tapes later, but for right now, we're just gonna let it go. Yeah. Okay. Okay, this is the question you're trying. So we get ln of y equals, and then we get 3 ln x plus 4 minus half ln x squared minus 3x, plus, minus 5 ln 2x minus 3. We're going to get y prime over y equals 3 over 1, 1 over x plus 4, plus 1 half, 2x minus 3 over x squared minus 3x, minus 5 over 1, 2 over 2x minus 3. We're going to move the y up. Then we get y prime equals that. X plus 4 cubed, square root x squared minus 3x, over 2x minus 3 to the 5. And then I get 3 over x plus 4 plus 2x minus 3 over 2x, x minus 3, plus 10 over 2x minus 3. Okay, we're looking at example 5 in the notes. Y equals x to the x. The most basic of the logarithmic. So, there are two reasons why. There are good kids at candy stores, and it's like fun fidget box. There are two reasons why we have to do logarithmic differentiation. Everyone should be paying attention. One, when I ask you to do logarithmic differentiation, and it is one where you have like a product rule embedded in the quotient rule. The other one you never ever spot. Most people will leave it on the test, they won't know what to do with it. It's when you have a variable base to a variable exponent. You know we've had variable bases to numerical exponents, so we just use power rule. Or we've had numerical bases to variable exponents where we rewrite it along the base derivative of the exponent. But we've never had to do, oh my gosh, this. So we are going to try and get that exponent to come down. So we're going to ln both sides. And what's the rule with the exponent? Comes out front. So we're going to get ln of y equals x ln x. Now what people often do not do is they often do not put the multiplication dot between them. So we have this here, x ln x. Do you see how I put the dot in the middle? Most people don't put the dot in the middle, and then you guys don't do product rule. Example 5. So we get y prime over y equals, and then we have to do product rule. So g, which is ln x, f prime, which is 1, plus f, which is x, and the derivative of ln x is 1 over x. So these cancel off. Does that mean you get 0? Or what does a slanted line know? It's just it's a 1, right? So we're left with y prime over y equals ln x plus 1. And then we have to move our y over. So we get y prime equals x to the x on x plus 1. Okay, here's two questions. Okay, so we have ln of f of x. Oh my gosh, the board doesn't even want to work anymore. Ln of x e to the x cubed. E to the x cubed drops in front, so we get ln f of x equals e to the x cubed times ln of x. If you put the multiplication dot in, most people will do well on this. So then we get f prime of x over f of x equals g times f prime, which is 3x squared e to the x cubed, plus g f prime f g prime. So we move this up here. So we're going to get f prime of x equals x e to the x cubed. E to the x cubed can be taken out. Ln x 3x squared plus 1 over x. Finito. Okay, this one, we're going to have ln g of x equals sine 2x squared times ln 3x.
Mrs. Lepp, Brooklyn has my phone.
So then we have g prime, oh gosh, g prime of x over g of x equals g f prime, oh gosh, my board doesn't even want to write anymore, it wants to be on Easter break, cos 2x squared times 4x plus 3 over 3x, which is 1 over x, sine, it really is not working, 2x squared. Okay, and then we're going to get g prime of x equals 3x sine 2x squared ln 3x cos 2x squared 4x plus sine 2x over x. 2x squared over x.